Okay, good afternoon. My name is Ram Ramasubramanian. For those of you who don't know me or haven't had a chance to meet with me, I'm the Vice President for Research here at UVA. On behalf of the Provost and I, Provost-elect and I, and the directors of the directors and staff of the Pan-University Institutes, I'm pleased to welcome you to this inaugural lecture in the Building Bridges lecture series. President Ryan, in his first address to the class of 2022, had the following advice for UVA's newest students. Don't be afraid to engage with people or ideas that are different from you. It is one of the best ways to sharpen your thinking and even change your mind. He said, when in doubt, build a bridge, even if you're not sure where it's going. This lecture series is intended to help build that bridge among our research community. When researchers from disparate disciplines focus on a common societal problem or need, possibilities for innovation and solutions to some of the most challenging aspects become possible. The intention of the Building Bridges lecture series is to showcase the cutting-edge interdisciplinary research in order to exemplify how the whole is greater than sum of the parts. One of the challenges in pursuing interdisciplinary research is the lack of opportunities to learn about the capabilities of fellow faculty members, congruent and counterpoints of view to that of your own, and all the talent surrounding us. This series will also provide the opportunity for informal peer-to-peer interactions. After the lecture and the Q&A is over, you have an informal session, and nurture future collaborations among UVA faculty to pursue impactful research. Now, I'd like to welcome Professor Alison Kress, Director of the Global Infectious Diseases Institute, and Professor of Microbiology, Immunology, and Cancer Biology, to introduce a distinguished speaker for this afternoon. Alison.
Thank you, Ram. Good afternoon. On behalf of the Pan-University Institutes, welcome to this inaugural Building Bridges lecture. I'd like to thank Linda Columbus, who's Associate Director of the Global Infectious Diseases Institute, for discussions that led to the creation of this series, and David Garcia, Amy Fansler, Jonah Vogel, Danielle D'Andrea, and Carrie McGowan for bringing it to fruition today. So I'm pleased to introduce today's lecturer. Dr. Madhav Marathe is a Division Director of the Network Simulation Science and Advanced Computing Division at the Biocomplexity Institute and Initiative, and a professor in the Department of Computer Science here at the University of Virginia. He has published more than 300 research articles in peer-reviewed journals, conference proceedings, and books, and he has over 25 years of experience in project leadership and technology development. His research interests are in network science, foundations of computing, artificial intelligence, human and engineered intelligence at scale, computational epidemiology, socially coupled system science, and high-performance computing. So hopefully you found something of interest to you in one of those many topic areas. Before joining UVA this past summer, he held positions at Virginia Tech and Los Alamos National Lab. He is a fellow of the Institute of Electrical and Electronics Engineers, the Association for Computing Machinery, the Society for Industrial and Applied Mathematics, and the American Association for the Advancement of Science. And he was the 2011 inaugural George Michael Distinguished Scholar at the Lawrence Livermore National Lab. So welcome to Dr. Marathe, and please join me in welcoming him for his lecture today.
So thank you very much, Alison, for the kind introduction. And it's a distinct honor and privilege to speak at this inaugural Building Bridges lecture series. And I couldn't have found a better place to speak. I'm thankful for you all for that. As Alison said and Ram said in his remarks, my goal is to talk about the work our division, but more broadly our institute, does. And to begin with, I would like to thank many folks who are part of this whole initiative. The directors of the institutes themselves and the funding agencies who have funded us for the last 25 plus years as we embarked on this journey. But perhaps most importantly, I would like to thank my colleagues, my friends and colleagues in the Institute and in my division who have made possible that I stand here and give this talk. This work is certainly not something that I have done alone. In fact, as time goes by, my contribution to this whole effort gets smaller and smaller. I think it's really a team science and transdisciplinary effort, and hopefully by the end of this talk, you all will be convinced that this is a wonderful way to carry on doing research that is certainly not possible for a single individual. So with that, I would like to start. I would like to just point out that the folks in the lab, and we have about 70 folks if you include our students who are still back at Virginia Tech and finishing their degrees, come from various backgrounds and disciplines, from computer science to business to economics to sociology to biology, public health, electrical engineering. All these faculties are represented in our group, and that should give you a sense for how this team works. So what we are interested in a nutshell, is to understand the conceptual, the theoretical, and the technical issues related to understanding very large and massive biosocial and technical systems. These co-evolving systems are large enough that you cannot understand them by simple analytical formulas that oftentimes can be done for smaller systems. And they're not so large that you can use reduction principles that physicists have developed over the last 200 years to build reduced order models. Furthermore, these systems have layers of interactions built into them. And a fundamental aspect of these systems is that they're networked. And these networks really govern the way the individual agents or nodes interact with each other. Furthermore, they co-evolve with the dynamics. As a result, these things are not stationary in time. Let's take a couple of examples that hopefully will tell you the kinds of systems that I'm going to talk about. From mega cities that are being developed right now, and should I say, not really developed, but they're really emerging out of interactions, not in a typical way that folks have gone on planning large cities in the past, to natural and human-generated social habitats, to the immune systems, to the financial markets. All these are examples of the kind of systems I'm going to try and allude to today, and hopefully you will see an interesting pattern in understanding these systems. These problems that arise in studying the systems range in a way that a single person really cannot address them in any effective manner. Let's take a couple of examples again. If I were to try and undertake the question of detecting or responding or reducing the impact of next pandemic outbreak, you would certainly agree that, wow. I'll continue, and you'll certainly agree that it is not possible that these problems can be solved by either a single person or by even a small group of people within a certain department. And that's the question that we are after here today. The team undertakes a transdisciplinary team science approach to try and understand the basic principles that underlie these systems and tries to develop practical solutions, but rigorous solutions, so that they can be used by policymakers to try and make a difference in how these systems are built, understood, and refined as we go forward. I'll continue without the slides. Hopefully, I can wave my hands. Oh. Anyways, it's magic. So let me just first tell you what I think is transdisciplinary science, and luckily, I didn't have to go too far. There's a whole field of transdisciplinary team science, which I'll call TTS for the rest of the talk, that folks have developed, is in fact a science of this. And Kara Hall at NIH has been a big proponent of this idea. They've tried to put in big programs at NIH to understand how team science is done and how transdisciplinary team science is done. So I've tried to borrow and modify a definition that Rosenfeld and Kara had given in their paper. And what they said here is it's a process in which a collection of individuals with expertise in different fields work together over extended periods by synthesizing and extending discipline-specific theories and concepts to create new approaches and methods to address a common problem. It's a really nice definition. It tells you that you're trying to come up with new approaches and methods that cannot be done in a siloed manner. It's trying to talk about collection of scientists rather than a single scientist. Now they leave out the definition of what team means. And of course, a team can mean a bunch of 3 or 4 scientists or a much larger team. If you study Large Hadron Collider, that had probably 1,000, maybe 10,000 folks forming a team. Their Human Genome Project that had teams that span multiple universities and countries. And then there are smaller teams. The size of the team, of course, depends on the questions people undertake. Such a science has certainly not been something that folks have done for a while, right? And I wanted to, again, take this example that Ledford in her article in Nature had talked about, and I've tried to paraphrase a number of things she said in the article, which I found very telling. So Theodore Brown, who set up the Beckman Institute at UIUC, decided to set up this institute when Beckman, their alumni, wanted to donate about $40 million to the institute. And he wanted to, and this is a paraphrase of what he said. He said, the problems challenging us today, the ones really worth working on, are complex, require sophisticated equipment and intellectual tools, and just don't yield to a narrow research approach. The traditional structure of university departments and colleges was not conducive to cooperative interdisciplinary work. And it encountered a lot of resistance at UIUC when he tried to set this up. And again, there are quotes. Department heads fretted that faculty members and their grants would be snatched away. Certain folks said that you only do transdisciplinary science if you can't excel in your own field. Folks were worried about space and resources. And despite this, and luckily for Theodore Brown, Beckman really liked this idea and provided a full $40 million asking price to set up the Beckman Institute at UIUC. It was the largest donation at that time from a single private donor to set up such an institute in US universities. And this aspect has actually continued since 1983. We have a number of other institutes that have been established, from the Santa Fe Institute to Genelia Farms to Koch Institute, the institutes on the campus here now that have been established. All of them talk about similar questions. There are a number of academic reports and articles, from this special issue in Nature to articles in the National Academies, the Swedish book that came out called The New Production of Knowledge, all allude to this. And Dr. Ram here actually authored one of the reports, as I understand, when he was at NSF on convergence, which is quite related to this. So we have made a lot of progress in the past 30-odd years, but multiple challenges remain. And hopefully, during my talk, I can tell you the way we have approached this problem, the success we have had, the challenges we have faced, and hopefully by the end, you will all be convinced that maybe this is a topical area that you folks want to pursue. And I think for folks who are here today, I have no doubt in my mind that you really want to do this kind of science. And I'm just being an evangelist effectively in trying to sell this kind of work. So our approach then consists of approximately 5 steps. And I broke it down into 5 steps to make it easier. They are not linearly ordered, but certainly 5 components. And again, there was a nice article in Nature, the same special issue by Rebecca Brown and her colleagues. And I can confess that I did not look at that article before making my slides, but found a rather amazing set of similarities between the things she and her colleagues called out in what the components are. The first component is to have a common goal or mission. If you don't have that, usually these things don't work out very well. I spent my time at Los Alamos. Clearly the program there that led to the weapon there was one that had a common mission and had a time associated with it. The lunar mission in 60s was another one that folks did. So I think mission is important. Having a common goal is important. Second, and importantly, sustained and stable funding sources. Oftentimes you get small pots of money for small periods of time, and this is not how you would be able to do science of this kind. Third is to nurture a culture of diversity and respect. Usually, you get people from various fields. They have different value systems. And it's important to try and nurture this kind of culture and accept the diversity that comes with it. In our work, we find that oftentimes teams have to be grown bottom up. Now Chris is going to talk in the end for a few minutes, and there are exceptions to this rule, but in general, we find it's easier to bring in people when they're junior and essentially expose them to the team science culture that we have developed and let them grow within this unit. And finally, it is important and interesting to do this science in the context of working with policymakers and end users, because they, in the end, drive the questions that they're after. And those questions then can be the basis of the way we do the science. So how successful was our approach? I will also talk about where we failed. So this is just one part of the story. But I think on the whole, this approach that we followed for our group was quite successful. It was successful from the standpoint of funding. We've been funded over $300 million from our time at Los Alamos to Virginia Tech and here now. Our group has written over 500 articles. We have had more than 40 PhD students, a number of master's students. We have created stable and nimble teams that have diverse skills to go after large projects and problems. We were able to execute transdisciplinary projects that many other teams simply could not. And finally, we made fundamental contributions to science, engineering, and policy. And I'll give you examples of it. I wanted to tell you a couple of important insights and I think Chris is the one who gets the credit for these insights that he pointed out to me. One is that usually science of this kind is done when you work with operational agencies with a practical mission-oriented need. It's usually hard otherwise to put projects like this. So you require what he calls unconventional sources of funding. Second is the project planning part. On one hand, you want these projects to be rigid enough so that you can feel that you're making progress and you can measure the progress. But it has to be flexible enough so that you can dynamically incorporate the needs of the sponsors themselves. So what are the challenges that we faced? And these are real challenges I'm sure you folks have faced as well. We oftentimes found recruitment and career growth to be a non-trivial challenge that we had to face. And it's because the metrics that traditional academic units have do not find this kind of science to be one that it makes it easier for them to measure. They want to encourage it, but they simply are not able to measure and value it in a form. We sometimes did find keeping the funding stable and sustained. Although this has not happened too often, we did have certain periods where we were certainly challenged. Third, we found that training individuals in these fields is non-trivial. So again, I've taken this from articles that others have written, but the basic idea in sciences these days is to move from an I, that is the person who's deep in a field, to a T, where a person is deep in a field, also knows a number of other fields, to finally a pi, in which you're deep in two fields, and know a lot about other fields. And this is the basic form of expertise you want to develop so that you can essentially have cross-pollination in terms of ideas. And finally, and I think quite importantly, and something again that Chris has pointed out to me repeatedly in our discussions, is when you do this kind of work, at least in the early phase, this doesn't lead to consensus science. It's very hard to convince your peers and your fellow researchers that this is new and interesting, because this is not so well defined in a typical manner that we are used to in an academic setting. So I want to outline the basic technical elements of our program here, and then we'll take some examples. So we have developed a set of core competencies that are in the middle here, which includes synthetic information systems, and I'll say a little bit more about it in the next slide. Expertise in machine learning and AI. How could I not say that anymore? All of us in computer science certainly have to talk about it. Network science, that's something that all of us have been doing. High performance computing models and analytics, and cyber infrastructure, building large scale computing systems. And the topical areas, the application areas that our group has focused on, has four basic parts to it. interdependent infrastructures, health sciences, systems biology and informatics, and social, behavioral, and cognitive sciences. And hopefully I'll be able to touch on examples that connect all these pieces together. So I have distilled the work that we have done for the last 25 years in terms of our approach in 3 slides, and hopefully I'll make good sense of it here. But effectively, the first step of the work that we do is to take diverse data sets that we can lay our hands on, open, things that we have to buy, to build what you would call a virtual representation of the system that we want to study. This representation is such that it's at scale. So if I want to study the immune system in the gut, I would try and represent every cell if possible, or close to it. If I want to study a city, then I would represent every individual human in the city. If I want to study animal populations, then I would like to represent as many of them in the simulations. It's done at scale and at very high resolution. These are called synthetic information systems. They're synthetic because you synthesize this virtual representation by combining lots of different data sets. There is no single place that you can find this integrated data sets, right? In fact, oftentimes people don't want you to give these data sets. Secondly, it's synthetic because, and this is very important in today's information age, if you study humans, and we do study epidemics and infrastructures where humans are an integral part, then while we have a virtual representation of the city and statistically looks very similar to a city, no individual agent in our virtual world is identical to a agent or a person in the real world, okay? But statistically, they are very similar. And we have done this deliberately and out of choice. The reason being that for privacy reasons and many other reasons that we all know right now, you don't want an accurate representation of that individual. You want the accuracy which is statistical in nature. And later on, after the talk, I'm happy to tell you what that means in a very precise manner. But this is important to understand. So while we started this work back in 1993-94 through a project called TRANSIMS, which I'll say a little bit about, my colleague, Dick Beckman, and his friends created the first set of methods to create the global synthetic populations. And from then on to today, we have reached a state that we can actually build inside our computer a virtual representation of essentially the entire global population. 7 billion agents, 28 billion interactions on a normative day, 220 countries. And this data structure is extremely powerful. You can now study all sorts of different questions with a data structure of this kind. And it's a real nice and interesting computer science problem, of course, but it's a problem in social sciences, it's a problem in demographic sciences, it's a problem in health sciences to bring these systems together. The second step is to take this virtual representation, which is static, effectively speaking, and essentially put it in motion, have dynamics over it. The kinds of dynamics we would study is certain kinds of diffusion processes. How would infectious disease spread? How would a financial contagion go through it, like the bank failures? How would a meme spread through a network? How might news on the internet, real or fake, and it's important, real or fake spread through this, and how can you detect it? These are all important aspects, and again, what we started out as a very modest effort during our early work has blossomed into a very, very interesting set of simulations. To give you a sense of what we can do today, we can simulate at the level of individuals entire season of flu, which is about 200 days, in a country like US with 300 million agents and 15 billion edges or network interactions on a system at Lawrence Berkeley Labs as well as Lawrence Livermore Labs, which has got about 700,000 processors on the system in about 10 seconds, okay? That's the kind of scale that we have achieved in terms of these simulations. And the reason we do it, of course, part of it is fun as computer scientists, but other reason is these systems are stochastic, and single run make no sense at all. You need to build these large stochastic simulation and ensembles of them to try and reason about these systems in an effective way. The last bit is building apps and cyber infrastructures. Once we do these systems and produce these analytical results, we find that end users don't really want to become computer scientists. They really want to want to follow their field and want to be focusing on that. And we learned the hard way, which I'll say a little bit later, wherein we say that building these apps or infrastructures where it makes it very easy for end users to do their science is the only effective way to interact with them in terms of daily use for these tools. So let me give you a few real-world examples in the time that I have. And then hopefully I can have some time for question and answers as well. So I chose these examples for a reason. They certainly represent the group's history back from my time as a postdoctoral fellow at Los Alamos, where Chris hired me at Los Alamos, where he was a group leader, and led a project called TRANSIMS that I'll talk about, to a very recent piece of work that we've been working on in our lab here. So I take an example of a system that we built from 1991 onwards, approximately, until 2001. My colleague Stephen Eubank, who will also speak for a few minutes at the end, was a partner in crime with me and Stephen, and many others. So to give you a sense for all the things I said, let me try and elucidate how we went ahead and did this work. So TRANSIMS as a project did not arise because we wrote a grant to NSF. In fact, Chris was the person who wrote that grant finally to DOT. But it came about because there were some very important national level questions that were being posed. Questions related to traffic flows, questions related to household behavior when infrastructure changes happen, assessing social justice issues with proposed infrastructure changes, and the environmental impact. For instance, EPA had been just stood up, and a big question was to try and measure or estimate the emissions that the car's traffic produces. Turns out that the traditional way, which is called the 4-step planning process, would not give good estimates of the emissions that these vehicles produced. And one big reason for this is that emissions are usually produced by vehicles when they accelerate and stop. So the start and stop aspect of the traffic is fundamental to the emission production, right? But if you take a 4-step process which averages out the flow and looks at them as average number of cars with average speed going between zones, you simply cannot capture these emissions. The second thing that a system like this allows us to study are emergent traffic jams. This is a well-understood problem in physics under the name of emergent behavior, where a small perturbation can cause traffic jams and you never know who caused it, right? We all curse somebody else in front of us saying that the accident was caused by them. But these small perturbations in complex systems like this cause very complicated dynamical structures. And systems that we built out were an attempt to understand this. There are new uses of this that we did not think about it then, but certainly are very relevant today, which is about autonomous vehicles, where you can study how these vehicles would be put into traffic. And in my opinion and judgment, the technology to build such cars is, of course, here now. There is no question that we can do it. The hard part, which might never allow us to have all the vehicles put on the road, is the legal issues and indemnification issues. And Kevin, who is here, certainly understands this from a legal framework. And we think that this is a question that systems like TRANSIMS can be used to understand. They can be understood as interaction between vehicles. So for instance, when we are crossing the road, oftentimes, at least coming from India where traffic is really notorious, if a car is coming my way, I have to be very thoughtful and essentially play a two-person game in my mind to decide whether I should cross and the person is going to stop, or this person is not going to stop even when he sees me halfway through the road, right? Now, the autonomous cars have built-in safety standards. If you know this, it's not very clear. And once people know that the cars always stop because they know that the cars have to stop because that's what they're programmed, people might never stop crossing the road, even though it might be dangerous otherwise, right? This is just a simple example. Or another example of an accident. Where do you indemnify? Was it because the software system, or the driver, or the interaction between vehicles? We see this issue in the aircraft, the 2 accidents that happened to the Boeing MAX airplane. Very similar issues, right? So the requirements were set by government agencies, and we did end up doing a number of case studies to try and improve our models over these 10 years and try to build, and I'm going to play this movie if it plays, try to refine the systems. So TRANSIMS has been used not just by us, but after we finished the project, by a number of different transportation offices, metropolitan planning offices, and I just give a list here. The one in red is the studies we did. The one in black, which I'll say a little bit about, is a study that we did partially, and the studies in blue were not done by us, but by others. This movie here is a movie that I took from the website that our colleagues at Argonne National Labs made this, and I'm told that they did this during the Chicago Olympic bid. Now, they didn't get it. I'm not sure whether the movie and the TRANSIMS was the reason or not, but certainly they used this to understand the traffic flows and congestion that might come up, right? And this gives you a sense for the kinds of simulations and systems you have to put together to understand traffic in such detailed manner. I want to tell you how the teams were, because I told you that this is an example of transdisciplinary team science. This had about 15 to 20 individuals working closely, and a level 1 network of academicians who work with us for short or long periods of time, from folks at universities to the National Statistical Sciences Institute to the government offices. The background of scientists was very varied. Science, statisticians, physicists, civil engineers, transport engineers, air chemistry modelers, etc. We were all proximal in Los Alamos, but not in the same offices. The components were, again, designed to work independently for a period of time, but they were brought together by these case studies. And the stakeholders really defined the broad questions. We worked on this project for 9 years in rather direct manner, right? Very long time. And the project was evaluated every year by the National Academy's Transportation Research Board at the meetings. And Chris, in a large measure, and Dick Beckman took a lot of arrows in trying to defend this project, because it was always challenged as one that had a lot of interesting ideas, but weaknesses and reasons why maybe we should not proceed further. What I'm very happy to tell you is that TRANSIMS has led to very interesting technologies that I will say a little bit later about, and maybe for instance, this is the first time that urban synthetic populations were constructed and multi-layer networks were constructed. This was back in 1993. This was not very common then. First time people did discrete choice modeling of routes and used. So today when you start routing on your Google Maps to say when I walk for a while, might take an Uber and then walk again, this is an example of the kind of routing that you will do, and TRANSIMS developed this technology. We did large-scale simulations. That was again the first time that simulations of social systems at this scale were ever done. And finally, we had shown how air chemistry models and traffic models could be coupled together to estimate emissions, right? From a situation where 4-step process was the way science was done in transportation, to a state where almost any reasonable group in transportation sciences will use this particular paradigm to study transportation, is an example of the kind of success TRANSIMS has. Now, that doesn't mean TRANSIMS itself as a system is alive and doing very well. It has gone through a number of changes. But the paradigm has stayed, and it has completely changed how traffic science is studied in the field. Okay, and this is an important idea. So I want to give you one example of how a case study is done using systems like TRANSIMS. This was a study that AECOM led. We were a part of it for a short period, the first half, and then they continued. And the question that was posed to AECOM as a part of what's called the WATT study, the White House Area Transportation Study, was to understand or assess the impact of closing a perimeter, a road in and around White House. They had already closed a smaller inner circle, but after the 9/11 events, there was a desire and a good reason to close out another sort of bigger perimeter around the White House. This might seem like a fairly trivial question, but once you start thinking about the impact that might have on traffic, especially in a place like DC, this becomes a complicated question. And we are asked to study issues like building maybe an underground tunnel to move traffic, or adding more buses, adding new stops, adding bike sharing platforms. All these questions were brought in front of the group, which was studied using TRANSIMS and its extensions. And this became then a set of evidence-based answers that were used by policymakers. I can't quite tell what exactly was used and how it was used, of course. We have tried to stay out of that part, but was used to finally make the decisions in terms of how traffic is routed in Washington, D.C. So let me move to the second part of this, which is a somewhat more grim scenario that we studied, not so much for the scenario itself, but the disruption that we want to represent in this. This is called the National Planning Scenario 1. It's a scenario in which, and this is a scenario that is put out by the Department of Homeland Security, and the scenario asks for studying the impact of a very large nuclear device detonation in downtown Washington, D.C. And this problem is a problem that has been studied for more than 60 years in national labs. Right? It's not a new problem at all. There's a beautiful report by folks at Livermore Labs called Key Response and Planning Factors for Such an Event. But most of the focus of that group was on what's called prompt response for all these 50 years. They essentially accepted victims as passive, and the scenarios were Cold War scenarios. The number of casualties that people estimate in a scenario like this is more than 250,000. And you might think there's not much to plan, is there, after such an event that happens. But when you think about it, that particular area, the greater Washington area, has more than 3 million individuals. You suddenly realize that there are 2.5 million individuals still around, hurt, very worried, trying to take care of their families, and we need to plan and try to save lives and try to reduce the sense of worry that these folks have and build in place planning and response methods to do it. As a simple example, let's think about a scenario when such an event happens. And we have Fred, who's a virtual agent, and Fred is a part of this plume and has to decide where does he want to go? What path does he want to take? How is he going to get to his spouse? Will his kids be okay? For instance, one of the things that the previous report here talked about in Budemeyer's report was very interesting. The policy that has been put out, and I think many of you who are a little older know this policy is called shelter in place. So if you know such an event has happened, then the policy is to stay where you are and take shelter. I think it's an interesting policy, but think about the problems with such a policy, right? When you try to make it operational. First, most people don't know that this is the event that has happened. Second, we find over and over again through surveys, experiences people gather through hurricanes, through events in Japan, in Russia, that most people are not going to comply with such a policy. Most people want to know where their family is. Are they safe or not? Can I get close to them? So family reconstitution is a fundamental part of human behavior. So just because you tell me to stay where I am, I'm not likely to do that. Third, depending on where the plume is and how damaged my building is, I might actually have far higher levels of exposure to this event than if I had left that place and gone in some other direction, right? So theoretically, this is a very nice policy to put in place. But operationally, this policy is really very hard to put together. And that's the point I wanted to make here. So if you want to study Freds and 3 million Freds like this in a city, you quickly realize that a simple system cannot study this. You have to understand the complicated behaviors that go in to build systems like this and understand the interactions that go with it. So I have actually outlined the kinds of transdisciplinary advances we make, but let me just tell you a couple of interesting things that we suggested the policymakers consider, which is not in the slide, but I think is very interesting. One of the things we find is that it's not a good idea for first responders to go into the site which has been damaged. In fact, in many cases, they cannot reach. There's rubble, which is very high. There is glass. Many of the first responders have been hurt, have died. So that's not something that they can do. But we find that if you put on which is possible now, what's called COWS, cells on wheels, and build an ad hoc internet, which is now possible through advances in technology, then folks can use the wireless devices that they carry these days and try to connect and find out what's happening. So the biggest thing we want to try and do is to try to reach individuals and provide them information, because we feel that converts them from a passive or victim to an active responder itself. They also maybe are able to reach their family and reduce the level of concern that they might have, right? This is an important part of the story. Similarly, we find that it's important to set up these triage facilities in a manner that can then take care of folks who leave the town in an effective manner, right? So many such insights were obtained from these complicated simulations that we studied over a long period of time. I have about 5 minutes, and then I'll stop so that I can let Stephen and Chris talk. But I want to touch on a topical area on public health epidemiology, because I think it's a topic that many of you here might have interest in, and we've been studying this for a long time. We have built a system called Simdemics that allows us to study how infectious disease spread through populations, ways to plan so that you can detect when a pandemic is going on or it might start, ways to control it when the pandemic starts, and ways to essentially reduce the impact. And we've done a number of studies. I'll only mention one. Stephen is here. He and Chris played a big role in this particular study. This was a paper in Nature where, after the 9/11 event, there was a real concern of a biothreat event where a smallpox would be released in a city. And there's a paper in PNAS which said that maybe you want to vaccinate individuals to protect yourself. Turns out vaccination for smallpox is not without its problems, right? Most of the youngsters have not been vaccinated. I, coming from India a long time back, have been vaccinated, so we don't know the effects of a vaccine like for smallpox right now to immunocompromised folks who are older. So the worry was that you might actually cause more harm by doing a mass vaccination than the event itself. The last, and then I'll jump through the other studies, but the last study that we actually played a big role as a part of the DoD team is to work very closely with the DoD for the Ebola response efforts. We were the lead analytical group that supported the Defense Threat Reduction Agency as they were helping the national and international groups try to take control of the Ebola outbreak in Liberia. The UK and their groups were working in Sierra Leone and other portions. We built down forecasting systems. So maybe in the interest of time, I'll just flash the last bit for my friends and colleagues in the biological sciences group. A number of projects that have been taken up by the group here are of interest to many of you, I think. They relate from things that have to do with studying genetic markers to understanding whether small sequences of a genome could cause threat, to systems like Patrick that our colleagues in my group are leading for the last 15 years, which is a bioinformatic resource center and allows one to collect and study information related to bacterial genomes. This is a project that has been going on for 15 plus years, and NIH has spent over $60 million to build this infrastructure out, and is an amazingly interesting infrastructure that I encourage you folks to take a look at. My colleagues have been working on this really hard, providing a number of training sessions, building out tools. Rick Stevens at Argonne National Lab is the current PI of this project. And together, they built, I think, a very, very unique infrastructure for biologists to use. I'll summarize as to where we are heading, and then let Chris and Stephen take a couple of minutes each to say their thoughts. I think the technology affords us to take such a leap, where we think that it is possible to build what we call tools that are pervasive, personalized, and precise, so that people are empowered to make decisions, either at individual level or a collective level, at the level of a family or the level of a community, at the level of a city. And I think the technology allows us to do that. And we have started our work in three, I think, interesting research directions. One is sustainable and adaptive social habitats. sociome and One Health. The term sociome was coined by us to move away from the other omics and include social aspects to it. And the last part, which is very interesting for all of us here, is autonomous systems and man-machine symbiosis. We have to understand how humans and autonomous systems are going to interact. They are becoming part of a life, whether we realize it or not. It's like frog in the boiling water. We slowly are getting, used to and hooked to these devices to an extent that they are just part of us, in much the same way that the microbiome is part of us. And I leave you to think about the effects that this will have in the long run. So I'll stop here. Before taking questions, if it's okay with you, I'll let Stephen speak for a few minutes, and then Chris have the last word. I think they've been working with me from 1994. In fact, Chris hired me, so it's more than working with me. You've been working for Chris.
And Chris hired me as well, so he's got quite a group of people here with him today. I don't have slides. I'm just going to talk about some very concrete aspects of the broad team science vision that Chris and Madhav have been presenting. So one way to think about the kinds of research that we do in our group is that we look at at how collective phenomena depend on the mesoscopic and microscopic details of interactions in these massive systems. And this is not a new problem with us. It's a problem, though, that we've been forced to recognize because of dealing with these particular studies that we've got. It arises in every single study we do. If you want to control a system of interactions, you have to have some control surfaces to grab onto. You have to know what manipulating them will do to the whole system. So I want to think about some of the prerequisites for working on a research problem like that. One thing, for example, is we always turn to mathematical formalisms to describe the problems that we work in. But that's not enough, because this problem arises in social sciences, in physics, in math, in computer science, in different guises, and they all have formal mathematical methods for dealing with it, and they're all different. It's part of the jargon of the domain. So that's not all you need. You need more than just a formal mathematical description. Also, you'll hear people say, well, it's a wonderful environment in the Institute because you can walk down the hall and knock on someone's door and talk to them and get a completely different perspective on your problem. That's really useful. It's prerequisite, maybe, but it's not sufficient. In the teams that we work in, we can walk down the hall, knock on someone's door, and not only find someone with a different perspective, but someone who's been working on the same problem in the same area with a different perspective and knows in depth what that perspective has to offer the solution. It's not just, oh yes, I've heard that there's somebody else in my discipline who works on this problem. It's that they do it themselves. So there are those aspects. And ironically, one of the few areas where this problem doesn't seem to have been applied much is the problem of figuring out how to assign credit for work that's done in a team environment. Because I raise this because I think it's one of the big challenges facing an institution like a university that's trying to sponsor team science research. And I won't pick on the university too much, so I'll pick on NIH instead for some examples. It's very hard for them to recognize what a team is and what the members of a team do. As an example, after 10 years of being PI on this MIDAS research program out of NIH, I would routinely submit proposals to them and have them return saying, well, this is a nice proposal, but you really ought to put an epidemiologist on it. I'd been doing computational epidemiology for 10 years at that point, but I don't have the credentials that say epidemiologist. And they couldn't recognize it without that. So part of what you've been working with, if you've been working with the Institute, is understanding how we in the Institutes can establish our credentials to the outside world with the help of the colleges and universities that are existing. sorry, I'm trying to, got the wrong glasses here. Also, another thing that happens, I was really happy a few years ago to see the request for proposals come out of NIH that specifically said, this proposal is for a teamwork environment. We're looking for proposals that explicitly include members with these skills, and it listed like 6 different skills in areas that were really appropriate to the call. And then it had the budget, which was the budget for a single PI lab with a couple of staff scientists and a few students. They just didn't understand what it takes to support team science. And I think this is something that the university has come to grips with and is thankfully being very generous with supporting. I'm also remembering that at least back in the 80s and 90s when I quit being a student, there was a lot of discussion about how to prepare students for work in industry that required working in teams. When you've brought them up through this very competitive environment, always assessing, grading, separating the good from the bad, and I lost track of that discussion. I was very fortunate to grow up in an undergraduate environment that was seminar-driven and external examiners, so we didn't have quite that competitive nature. And it made a difference when I got to grad school. But I don't know if we've applied the lessons of that kind of pedagogy to ourselves, to the departments themselves. When I look around at the junior faculty who come into the institutes, I see problems as simple as whether you get credit for journal articles or conference proceedings, peer-reviewed conference proceedings. And there are departments that don't understand that these different criteria apply to different people. There are issues with sole authorship versus team authorship. We don't really like sole authorship in a team environment because it means that somebody's sort of not really involved in the team effort. As the folks in the business school will probably tell you, you get the behavior that you incentivize. So if your promotion and tenure guidelines are all about these things and they don't take into account the benefits you gain from doing this kind of team science, you won't get the team science. I understand that that's what the institutes are for specializing in, but it's a cultural change. And we certainly don't have all the answers. I think Madhav has shown you that we have a sort of constructive proof that this kind of thing is possible and it's very valuable. So now I'll turn it over to Chris for some closing remarks. Chris?
Well, I'm a big fan of the Gettysburg Address, and that took 2.5 minutes, so I'm going to try and do that. So first of all, I'm always humbled when I look at all this work that's gone on in this particular division, because this division is something that obviously, this is the 8th instantiation of this group here. The 8th. It started in 1986. And it's been repeatedly reinvented. This is much, much better than it was in 1986. I can tell you that. But first of all, these wonderful examples are what we call in the Institute verticals. They're fundable problems that we do solve for people and generate science programs underneath them. Those produce horizontals. The real interest of the science program in the Institute are these horizontals. And the validity and the importance of that work and the choices that we make are driven partially by interest, but they're heavily driven by these verticals. It's hard to describe the horizontals, and so we talk about the verticals a lot. a lot of these verticals, there are multiple ones you saw. There's population dynamics, there's infrastructure analytics, there's system biology and is associated with infection and epidemiology and many other reasons. But those are verticals in this division, and they come together in a certain way with these massively interacting systems. We have other divisions. At the moment we have 3, but we intend to have 6 by the end of this on-ramp. They fill out the vertical coverage of these horizontals, this basic underlying work that enables these verticals to exist. If we had to start from scratch on every one of these projects, we would never get anything done, you see. And so being able to go down the hall means that you're on the same horizontal. You're talking to somebody in the horizontal that you need. That's what that means. So all I'm saying is that that's important. We also have student programs, which I'd love to tell you about, and I won't. And the incorporation of students is one of the most important niche advantages offered by inclusion of these kinds of institutes in universities. We will not give degrees. Departments give degrees. These students have to earn their degrees in departments, but they will work as researchers with researchers. Our grant density is high. We have lots of PIs as a function of how many people work in there in the thing. So we have a lot of differences. We have a sign on our wall. I'm going to get it made that says, I verify that I have worked with others and I have given help to every single thing I do in this institute. It is a very, very different environment. We completely respect the educational certification environment. We do not want to replace it or criticize it or anything else. We want to integrate it into the operation of a research institute, because at the national labs, at the federal labs I worked at before that, whether it's a cloak of secrecy or it is proprietary work or it is the lack of students that you own that just come visit maybe, we have a huge advantage here, a huge advantage, and we should take advantage of it. And we're very, very thankful to be here. We're looking forward to working with as many people as we can, and Madhav is a wonderful example for, I guess, the bottom-up growth of this sort of thing. I will say that when we hire a new division director, it's not going to be usually bottom-up. In Madhav's case, it took 20 years or something. We don't necessarily have 20 years all the time. So for our new division directors, we're often looking for very, very capable top-down hires. But for the most part, yeah, it's students, everybody is engaged with us. So thank you very much.
I think I'm done. I really appreciate you folks coming here. I hope this was useful, and I'm happy to take a few questions. You can tell me when we should stop, Allison, but I'm happy to take as many questions till then. Somebody at the back, I think, had a question before I. Okay, Chris answered. Okay, cool.
Did you have a question? No, not anymore. Okay.
Yes.
Public, and if so, are there any useful skills that you can, share with us?
So the question was, does diversity help you in communicating with other scientists? I think absolutely. Absolutely, that's true. I came from a computer science and math background, and I had a tough time initially communicating my ideas in certain kinds of setting. I don't know what tips I can give you, but the fact that you have to be immersed in that environment for a period of time and develop a common language and a framework that constantly tells you that there are different aspects that are important too. But I don't have any other sort of very clean recipe for doing it, excepting to do the apprenticeship within team science environment. Yeah. Really good question. Yes, it has. In traffic, it has resulted. In epidemiology, it has resulted. I think the concept all has to do with the language of networks, at least to me. And I'm sure if you talk to a physicist like Stephen, he would look at networks but talk about the same concept in a language that he's comfortable, and that's actually good for us. So for me, the concept has to do with what I would call algorithmic feasibility of implementing this, right? And we think that this algorithmic lens or a procedural lens or a constructive lens that has to be put on completely changes how the problem actually looks in the first place, okay? It provides resource bounds and considerations that you would have never otherwise considered in such a situation. A policy like vaccination, for instance, which might say, let's vaccinate everybody who is, from simulation tells me these nodes are important, vaccinate them. But there's no operational significance at all. Furthermore, finding these people who are very important and critical is very hard to do. So we think that there are solution schemes that the abstraction as networks and using what we call a computational or algorithmic lens provides, at least from my standpoint, and then Stephen would say the same thing from a physics standpoint, gives us. And I can give you more examples later. Yeah. Okay, thanks, Allison.